Rotational dynamics 2. A uniform rod is pinned at one end. At the free end is an additional suspended mass. The system is released from rest with the rod initially horizontal. Determine the initial angular acceleration of the system. We want to use here Newton's second law for rotation. The net torque is equal to the moment of inertia of the system multiplied by the angular acceleration of the system. This moment of inertia, this is a combination of two moments of inertia. We have a rod here, but then we also have essentially a point mass that's at a distance of 2 meters away from the rotational axis. So what we need to do here is we need to say the total moment of inertia is the moment of inertia of the rod plus the moment of inertia of, I'll just say, the 3 kilogram mass. The moment of inertia of the rod is 1/3 ml squared. We can get that from a table. And for a point mass, it's the mass times the distance away from the axis squared. So all of that means that the total moment of inertia that we are dealing with here is going to be 1/3. The mass of the rod is given as 6. The length of the rod is given as 2. And then for the 3 kilogram mass, m is obviously 3. And then the distance away that it is from the axis is 2 meters. So that right there, that is your total moment of inertia. That will need to be multiplied by alpha. Can we do this in our head? What does this come out to? This is 2, that's 8, and that is 12, so that's 20. 20 times alpha. That's what the right side of the equation boils down to. How about the net torque? The net torque, let's look at the picture again. What we have here, if I can scribble over the picture a bit, is the mass of this rod is 6 kilograms, which means it's effectively going to have a weight of 60 newtons right there at the center for the purposes of determining the total torque. And on the end here, this 3 kilogram mass is going to be pulling down with a force of 30 newtons. So we've got one lever arm for the rod, and then we got another lever arm for the 3 kilogram mass. So I think we're going to have to go 60 times this distance will be 1 plus 30 times 2. So on the left side, we're going to go 60 newtons times 1 meter of lever arm plus 30 newtons multiplied by 2 meters of lever arm. That's going to be 120. So I think alpha is going to be 6. And what are the units for angular acceleration? Radians per second squared. Now, is this answer constant with time? And that would be no. It is not constant with time because the torque isn't constant. And by Newton's second law, if the torque isn't constant, then the angular acceleration can't be either. Now, why isn't the torque constant? Let's scoot back to the original picture here briefly. And I'm going to completely mess up this picture, but here we go. This rod, pretty soon, it's going to be bent down like this. The 3 kilogram weight will still be pulling there, and the 60 newtons from the rod will still be pulling there, but now, check it out. Lever arm, not the same as before. This lever arm, not the same as before. And for that reason, the torque isn't constant. And if the torque isn't constant, then the angular acceleration can't be